So the first page is more being able to count. So the gray, I have to remember, the grays are the titanium. And so the titaniums, the titaniums are the corners. So 1/8 of an atom times 8 corners, and then plus 1 in the center. So you end up with 2 titaniums. For the oxygen, which is red, you have the X's are in the center. So you have 2 in the center. So whenever they're in the center, it's a full atom. And then this is a really weird one because the ones that we're doing the math for form pretty simple. The other 4 you have 4 faces, and a face, only half of it is within that qubit cell. So times 1/2. So that gives you 4 oxygens. So when we write the formula, we don't want to write it Ti2O4. Why? I haven't asked a why question in a while. So what's wrong with that formula?
We can reduce it.
Yes. I don't know who said that. Oh, was that Christian who said that? So we'd write it TiO2 would be the correct answer. And yeah, so how many titaniums? There's 2 titaniums and 4 oxygens in the unit cell. So it would be TiO2 or titanium 4 oxide. So for this one, it's a similar idea. The oxygens again are red. So you have 1/8 of an atom times the 8 corners, and then plus 1 in the center. So that gives us 2. We have 2 oxygens. And then the other ones, the silver ones, the coppers are all in the center. So you have 4 coppers. So our formula is Cu2O. And so the oxidation for the copper would be a +1. Remember doing oxidation numbers? All right. Oh, I forgot this is the one with all the different crystals. So fluorite, I should have worn my fluorite tonight. So the cations, the white, are FCC. So we have them at the corners and then one on every face. The anions are in, so I didn't talk about this, and I'm looking at my answer key because I never. So they're all tetrahedral holes. Sodium chloride is octahedral holes. I'm not going to ask you that question, but if you care, so the sodium chloride crystal or the sodium bromide, so when you do the lab for this week, it's all this math. So when they fill in these spaces up here and one in the center, so these, the green ones, are what's called a tetrahedral. And then based what is the formula? So the calciums, we have 4 calciums, so 1/8 of an atom times 8 corners. So on the second page, when we get into the math, you don't have to do it like this, but on the lab, there are questions where it says, show how many atoms there are. And so when I ask that, this is what I'm looking for. And then half an atom times 6 faces. So that gives us that we have 4 calcium atoms. And then the fluorides are all inside. So there are 8 fluorides in the center. And they're always whole cells. So our formula makes sense, CaF2, because we would expect 2 fluorides per calcium. You guys remember that from Chem 221. And then we're going to behold this lovely illustration. And this is, hopefully you're right, this is actually a really nice picture of what BCC looks like. So going from this corner to this back corner, it would also go through the center. And so this is BCC for tungsten. And cat is clawing me and is stuck on my shirt. Okay. And there would be 2. So there's 1 in the center and then the corners. So 1/8 of an atom times the 8 corners. If I will say, show me the work for that, but like for this, and when we do the back page and the worksheet, you don't have to show this kind of stuff. So if the edge is 316, so the edge means A, what I was calling A is 316.5 picometers. It wants us to find the radius. So for BCC, our formula is 4 radiuses equals the square root of 3 times A. So we would just plug this in and solve, and you should get the 137 picometers. No need to change it to centimeters for this. So a quick comment, when you're doing the math, whenever you're solving for A or radius, if you're in picometers, you should be like 100 or 200 or something like that. If you're in centimeters, this would be 1.37 times 10 to the negative 8 centimeters. So there is a point you start seeing the ratio without always going through the conversion, but it's a nice thing to know you're in the right ballpark. All right, was there any questions on that first page? This page is a little esoteric, but it's trying to, it's a nice page because it shows you the pictures, so you kind of try to visualize this idea of how they're all filling in into this lattice structure. All right, the math. So silver, which is like the very first one on your worksheet. Apparently I like silver. I gave you the radius and I gave you its FCC. So if this is our radius and its FCC, then our first step is you want to state the formula that 4 radiuses equals the square root of 2 times A. And you can keep it as picometers for now. Once we go to volume, we want to be in centimeters. So we would do 4 times our 165 picometers divided by the square root of 2, and that will give us a number. I think it gives you 407. Does that sound right? I did this all in one step, so I'm trying to find the pieces. Our second step is we're going to go to volume, but we're going to change that 407 picometers. Tristan, this is the step you kept doing wrong. And so if your volume should come out like 10 to the negative 22 or 1023. If your volume, ours is going to come out 10 to the negative 23 cubic centimeters. When you're in one dimension, it's easier to change. So our picometers to meters, so 10 to the negative 12, and then a centimeter, 10 to the negative 2 meters. So that would give us our 4.07 e to the negative 8 centimeters. And then we want to cube that. And that will give us our volume. So the A cubed will equal the volume. So you can break that into 2 steps if you want. I just did it in 1. So this is 6.76 e to the negative 23. And that should say centimeters cubed. Then our third step is it's silver, so it's 107.9 grams per mole. That's from the periodic table. That's why I have it right there. So silver, make sure you know your elements, right? Is and we get to use the Avogadro's number. So you can just write it like that, but remember you will want to divide it in parentheses. So you divide by that huge crazy number, and then it was FCC. So there are 4 atoms per FCC. And that will give us 7.167 e to the negative 22 grams. And then we would simply take the grams divided by the cubic centimeters, and you should get around 10.6. Yeah. And again, just number your steps. And you could have done this as the first step, step 2, step 3, the first step. The order These two have to go in order, obviously. All right, this one's BCC, and this is the edge. So this is telling you already that A equals 2.86 angstroms, which is going to be 2.86 e to the negative 8 centimeters. So you can walk through your steps. An angstrom, by the way, if you remember, is 10 to the negative 10 meters. But when we get to centimeters, it's always going to go to that with these because that's the size of atoms. And then A cubed is going to be our volume. So you can, I recommend for most of you that you actually figure that step out. But if you want, you can also just keep going and bring the density in 7.92 grams per cubic centimeter. And then this is per unit cell, or BCC. So 1 BCC is 2 atoms. And then Avogadro's number to 1 mole. So when it asks you what element it is, you want to end up with grams per mole. And again, you could break it into steps, or you can do it in one whole setup. And we should get around 55.8, which I'm pretty sure is iron. You would look on the periodic table, you'd find 55.8, and that's pretty much hits iron right on the nose. So you would tell me it is iron. All right, and then the last one, so this was just the 3 different, like what we did in our last week when I did the lecture, that we know it's calcium, so I'm going to start with that piece of information, that 40.08 grams per mole. Then we have Avogadro's number. So 1 mole is Avogadro's number of atoms. And it is FCC, so 4 atoms per FCC. And then I like to bring the density in, 1.61 grams per cubic centimeter. And that will give me my volume. So that's my first step, which is 1.65. Oh, that was the other comment I wanted to make. Sig figs are important. Sorry, this should be times 10 to negative 22, e to negative 22 centimeters cubed. So again, you keep seeing like a similar exponents on these. Please do watch and respect your sig figs. So usually you're going to have 3 or 4. My density is going to limit me to 3. Avogadro's number has 4. So if in doubt, you know, pick 3 or 4. But this one, because the density had 3 sig figs. You guys remember sig figs? Yeah. So that comes up, and we're going to be doing a lot of math tonight. And hopefully, yeah, and then this one also had 3. I don't know why. Oh, because our original number had 3. So all of these had 3 sig figs. All right. Once we got to this, my second step is we will take the volume to the 1/3 power. So it's the cube root, you can also say, and that gives you A, which is 5.49 e to negative 8 centimeters. And then you can do your conversion. That centimeter 10 to negative 2 meters. And that 10 to negative 12 meters is a picometer. So we'll have 549 picometers. So once you get out of the cubic, you can go back to picometers. When you're working in the cubic, you want to be in centimeters. Yeah. All right. And it is FCC. So since it's FCC, it is 4 radiuses equals the square root of 2 times A. So the radius would be square root of 2 times the 549 centimeters. So at this point, when you're plugging into these formulas, it is easier, that's picometers, sorry. It is easier to have it in picometers or angstroms, and then divide by the 4. And that's where I got my 194 picometers. So any questions? It was pretty efficient. All right, I'm going to stop that one.